This is going to be a fairly short lecture. It's a couple of applications of the determinant. So the first one is an application to computing the inverse of a matrix. So let's look at the 2 by 2 case. We know how to compute the inverse of A, B, C, D. We know it's 1 over the determinant times this matrix dA minus B minus C. So obviously the determinant plays a role here. But what about these things? You switch the A and the D and you change the sign on the B and the C. And the question is, what's that got to do with anything? And how do you generalize this formula? And here's how it works. So let's recall what the cofactors of a matrix are. The ijth cofactor is minus 1 to the I plus j times the determinant of the ij minor. And the ij minor is the one that you obtain by deleting the ith row and the jth column. And remember, this plays a role in one of the formulas for the determinant. Now, you make the cofactor matrix you start with the matrix A, and you replace each entry aij with the corresponding cofactor cij. That's called the cofactor matrix. So here's what it is. The cofactor matrix is the CIJs, where you have these determinants with the signs. So in the 2 by 2 case, for example, you replace each element with the one diagonally opposite to it. So it looks like this, and then also you have to take the signs into account. Those look like this, and what you get is D minus C minus B A, and that's the cofactor matrix. And that's beginning to look quite a bit like the inverse. Take the transpose of this matrix. That looks like this. And now let's multiply A times the transpose of the cofactor matrix. We get ABCD times this thing. And what do we get? We get AD minus BC minus AB plus AB and 0 and AD minus BC, which is to say you get the determinant times the identity matrix. And so up to the determinant, this is the inverse, which is to say A inverse is 1 over the determinant times the transpose of the cofactor matrix. So that's the general theorem. Suppose you have an n by n matrix, which is invertible. Then you take its cofactor matrix and call that C. And remember, that's the matrix whose ijth entry is plus or minus the determinant of the ijth minor. Then the formula for A inverse is 1 over the determinant of the matrix times the transpose of the cofactor matrix. Pretty neat, huh? So why on earth is that? How does this work? It can't be hard. It's just some silly formula. Let's see. So let's write out the matrix A, a few of the entries like this. And let's multiply it by the transpose of the cofactor matrix. And let's just look at the first entry that you get. So let's write down the first column of the transpose matrix. That looks like this. And when you multiply to get the first entry of the product, the first row times the first column is A11 C11 plus A21 C21 plus dot 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 AN1 CN1, and lo and behold, that's one of the formulas for the determinant of the matrix. So the diagonal entry is this determinant. But now what about the off-diagonal entries? I'm claiming those are all zeros. That's a little surprising. So let's look. When you do the first row times the first column, that's what I just did. I'm repeating that here. This is what you get, and this is the determinant. But what happens when you do the first row times the second column? Well, let's see. So the first row is these A's are still the same. It's just that the C's are different. They're C12, C22, and Cn2, for example. And I'm claiming that this is 0. Why is that? Well, look at the second row here, A12, A22. This formula that I've written down, it's as if I was taking the determinant of this matrix, except I substituted the first row into the second row and kind of used that by mistake, so to speak. And what happens is that when you make that substitution, I'm taking the determinant of a matrix where two rows are the same. And magically, you get 0. And that's it. That's why this formula works. Okay, let's go on to application 2. I mentioned this before, and so I'll just say it again very quickly. It's computing the volume of a box in Rn. Here's a nice box, and it's described by these 3 vectors, v1, v2, and v3, and they're not necessarily orthogonal. This could be a box which is not rectangular. And the fact is that the volume of this box, well, or in general, if you have n vectors in Rn, the volume of the box spanned by those n vectors is simply, it's the determinant of the matrix that you get by putting the v's as the rows. And let's see, that can't quite be right. It could be negative, so it's actually the absolute value of this number. So let's just do a totally simple example. If you have a rectangular box of size A, B, C, so then the 3 vectors are these, and you put them into a matrix and you get this, and lo and behold, the determinant of this box is ABC. So I'm not going to say anything more about the proof in general. That's the formula. Okay, one more application, and this is kind of a neat one too. Application 3 is finding the pivots of a matrix. So remember, if you have an n by n matrix, how do you find the pivots? Well, you start with the first pivot, is obvious, at least assuming it's non-zero. But then the next pivot you don't know until you've started doing your Gaussian elimination. And it's the entry which occurs here, and there's no obvious way to read that off directly from the matrix A. And determinants give you a way to do this. So let's look at, the 2 by 2 example, and let's say A is not 0. You do one row of Gaussian elimination. What do you have to do? You have to multiply this row, the first row, by minus C over A and add it to the second to kill that guy. And this turns into D minus BC over A. Okay. So the pivots are A and D minus BC over A. Okay, now let's get this over a common denominator. That's AD over A minus BC over A, which is to say AD minus BC over A, and there you have the determinant over A. Okay, so what do we see? If you call the first pivot P1 and the second pivot P2, we see that P1 times P2 is the determinant of this little 2 by 2 matrix. So let's go on and keep going. What happens here? So I just said P1 is A11, which is the determinant of this 1 by 1 matrix. And the next step is you see that the determinants here match up, which is to say P1, P2 is the determinant of this 2 by 2 matrix. And the next step is you look at the next size and you see P1, P2, P3 is the determinant of this upper left-hand corner, the 3 by 3 upper left-hand corner. And clearly that keeps going. So let's put that all together into a theorem. Suppose you have A, an n by n matrix. Let AK be the upper left-hand k by k matrix. Then, if the pivots are written P1 up to Pn, the fact is that the product of the first k pivots is the determinant of that k by k matrix. That's kind of cute. So that gives you a way to compute the pivots without actually carrying out Gaussian elimination. That's the key point. So for the way you extract a single pivot is you take a ratio of two of these determinants. So again, the key point is this gives you a way to compute the pivots without running through the whole Gaussian elimination algorithm. And I'll conclude with an application of this application, the application of the pivot formula. And it's the following. So remember, if you have a non-singular n by n matrix, there's the permuted LDU decomposition. PA is equal to LDU. And one question that is important is, can you do this, just have an LDU decomposition, which is to say you don't need the P. How do you tell? If somebody hands you a matrix, how do you tell at a glance whether it has an LDU decomposition? Well, remember, the way that happens is if all of the pivots are non-zero. Well, we know how to compute this. We just have to check all of these determinants. So the fact is that a matrix has an LDU decomposition if and only if the determinant of these upper left-hand corner matrices are all non-zero, every single one of them. So here's an example or a non-example. This matrix is non-singular, its determinant is non-zero, but the determinant of the upper left-hand corner is this little 0 here, is 0. And this matrix obviously does not have an LDU decomposition. So that gives you a way to determine whether a matrix has an LDU decomposition without actually carrying out Gaussian elimination.